Welcome everybody. Thanks to the program chairs for the invitation. I'm Alessandro Barenghi from Politecnico di Milano, and today presenting our point of view on the joint optimization of speed and security when designing code-based crypto systems with code families which rely on iterative decoding strategies. In particular, I'll be picking the case of LEDAcrypt. The team is listed here in strict lexicographic order. The goal of my keynote is to provide an overview on a design strategy and which are the trade-offs, how to design when you're designing a code-based crypto system and you want to pick sparse parity check metrics codes. Usually they go into literature by the name of QC-LDPC, MDPC, depending on how dense is the parity check metrics, because if you look at them from the decoding capability point of view, they have different properties. The point is here the density will be seeing that it's a security parameter. So my personal view is that what drives the density itself, the choice of the density itself, is the security bar. In these crypto systems, one of the main challenges is that the parameter space is not monodimensional. We have multiple parameters and they all influence the security. There are security equivalent choices for the parameters, and picking the best one is not immediately evident. The other two things relate to the fact that QC-LDPC and MDPCs are affected by non-negligible decoding failure rates if you use iterative decoding strategy. TFR is crucial if you want to achieve security against active attackers. And there are two challenges relative to this. The first one is that the definition of the delta correctness, which is the measure of the correctness of an asymmetric encryption scheme used in the most common in CCA2 constructions, is given a certain way, which is delta correctness. And this way of defining the probability of failure is not the same way you have in common coding theory when you consider the decoding failure rate of the underlying code. The fact that the decoder has a high DFR is a security concern, not just because the proofs don't work, but because there are active attacks exploiting a very high DFR. QC-LDPC codes are chosen typically in the McAleese and iterative crypto system. Why pick them? Well, because since they are quasi-cyclic codes, they have very compact representations. Essentially, you can represent the whole parity check matrix with just its first row. They have a good fast decoder via the common iterative decoding strategies. And the code itself has no other structure other than the sparsity and the quasi-cyclicity, because it's randomly picked parity checks along the code word itself. So essentially, I'll be talking about a code C, a QC-LDPC or MDPC code C, which is representable with a quasi-cyclic binary parity check matrix H, which is 1 times n tiling of circulant binary matrices of size P. So the row weight of the matrix is n0 V, and the column weight is obviously V because it's tiling of circulant blocks. And this is 1 block high. The code length is just n0 times P, the size of the matrix, and the code dimension is n0 minus 1 over P. So I'm picking the particular case where the code rate is always n0 minus 1 over n0. Now, T will indicate the number of errors that I'm expecting the decoding strategy to be able to correct with an acceptable probability. An acceptable means extremely high probability of correction. Let's start with tackling the challenges.